Welcome to lecture 17 on measure and integration. Today we will start the topic of integration. First I will explain the building blocks for the integration and how the process will be done. So, the topic for today's discussion is integral of non-negative simple measurable functions. See, the basic idea is we want to define the notion of integral for a function f defined on a set x taking values in r star. So, now for a function f, it is we can represent a function f as the positive part minus the negative part. The advantage of doing this is that f plus and f minus both are non-negative functions, and so it is and integration being a linear process. So, integral of f is going to be equal to integral of f plus minus integral f minus. So, it is enough to define the notion of integral for non-negative functions, and for non-negative functions f on x to r star, we recall that we can take it as we will look at functions which are first of all very simple functions. For example, let us look at a function f which is the indicator function of a set x of a set A contained in x. This is a function which takes only two values. So, indicator function of A is a function on x taking values in r star. So, chi of A at 0 at a point x is equal to 0 if x does not belong to A and is 1 if x belongs to A. So, one can think of this function taking only two values, right. Now, the value where it is 0, the integral. So, we want to define the notion of integral, and this is going to be with respect to a measure mu on x. So, mu a measure on subsets of x. So, we are going to write it as x a d mu. So, what it should be on A the value is 1. So, we would like to put it as 1 times mu of A. In some sense, mu of A is the size of the set and 1 is the height. So, this is in a sense the area of below the graph of the function. So, let us look at functions which are going to be linear combinations of indicator functions. So, we start looking at the integral of non-negative simple measurable functions. So, let us recall. So, we will fix our notation that from now onwards we are going to work on a measure space x S mu, where x is a set, S is a sigma algebra of subsets of x, and mu is a measure on defined on S, and this is a complete measure space. That means that all sets A such that mu of A is 0 implies that A and all its subsets are inside S. So, let us denote by L lower 0 upper plus to be the class of all non-negative simple S measurable functions on x. So, now let us recall what was a non-negative simple measurable function S. It is a function defined on x taking non-negative values, and it has a representation S of x is equal to sigma I equal to 1 to n A I times the indicator function of the set A I evaluated at x, x belonging to x, where A i's A 1, A 2, A 3, A n are extended real numbers, and the sets A i's are in the sigma algebra S. So, they are in the sigma algebra A i's are in the sigma algebra S, and they are pairwise disjoint. That means, A i intersection A j is empty for I not equal to j, and the union of these sets is equal to x. So, this is going to be the class of non-negative simple measurable functions. For such class of for functions in this class, we are going to define the notion of integral. So, for a function S in this class, if its representation is as given before, So, if S of x is equal to sigma a I indicator function of capital A I, then its integral is defined as S d mu. So, integral is noted by integral sign S of x d mu x to be a I, that is the value of the function on the set a I times the measure of the set a I, mu of a I. So, integral of S with respect to mu as written here is defined as sigma a I times mu of a I. A I is the value taken on the set a I. So, a I times the size of the set a I. So, mu of a I. Sometimes we do not indicate the variable x, we just write as integral S d mu to be the integral of the simple function S, non-negative simple measurable function S with respect to mu. And let us note here that our representation, the integral is with respect to a representation of the function. So, first of all we would like to show that integral S d mu is well defined. So, let us prove that the integral is well defined. So, let us take a function S belonging to L plus 0. So, it is a non-negative simple measurable function. So, let us say S is written as sigma a I indicator function of a I equal to 1 to n, also representable as sigma j equal to 1 to m of some b j chi of b j, where the sets a i's belong to the sigma algebra S, b j's belong to the sigma algebra S, and union of a i's is equal to x, and union of b j's is also equal to x, and these sets are disjoint. So, a I intersection a j empty and b I intersection b j is empty for I not equal to j. So, let us say that a set S, a simple function S has got two representations possible. So, what we want to show? So, we want to show that the integral of S, so integral S d mu is well defined, and that means what? So, mathematically that means we have to show that sigma a I mu of a I 1 to n is equal to sigma j equal to 1 to m b j mu of b j. So, this is what we have to show. So, let us start. So, sigma a I mu of a I equal to 1 to n, I can write it as sigma I equal to 1 to n a I, and then mu of this a I can be written as union of a I intersection b j, j equal to 1 to m, because union of b j's is equal to x. So, a I intersection x, and that is same as this. Now, this is b j's are disjoint. So, these sets are a I intersection b j's for I fix are disjoint. So, by using finite additive property of the measure, we have this is equal to I equal to 1 to n a I, and this is nothing but sigma j equal to 1 to m mu of a I intersection b j, right. And similarly, we can write the other side, that is sigma j equal to 1 to m of b j mu of b j to be equal to sigma j equal to 1 to m b j sigma I equal to 1 to n mu of a I intersection b j. So, the left hand side here is written as this sum, the right hand side is written as this sum. Now, we want to show that these two sums are equal. Now, let us observe that given that the function S has got two representations, this equal to this. So, how is this function calculated? At a point x, if x belongs to a I, the value is a I, and on the other hand it may belong to some b j, the value will be b j. So, that so that forces one to say that if x belongs to a I intersection b j, then a I must be equal to b j. So, this is the crucial thing to note here, that if S, a simple non-negative simple measurable function, is given two representations, one is sigma a I, capital A I, indicator function of a I, and sigma b j, indicator function of b j, then for x belonging to a I intersection b j, the value of S of x, on one hand it is a I, other hand it is b j. So, a I must be equal to b j. So, this is the crucial thing to note. So, let us make this observation and write it out. So, note that if x belongs to a I intersection b j, if x belongs to a I intersection b j, then S of x is equal to a I and is also equal to b j. So, a I is equal to b j, and if x does not belong to a I intersection b j, then S of x is equal to 0. So, that means in this summation, whenever x belongs to a I intersection b j, this a I is going to be equal to b j. Otherwise, in this sum that term does not matter. So, that proves the fact that, so that will imply from these two equations, from equation 1 and equation 2. So, this implies from equation 1 and 2 that sigma a I I equal to 1 to n of mu a I is equal to sigma j equal to 1 to m b j mu of b j. So, that is integral S d mu can be defined as either of these sums. So, is equal to either this or this is well defined. So, the integral of a non-negative simple measurable function. So, we can choose any representation of the non-negative simple function and define its integral in terms of that. Next, let us look at properties of this integral. So, we are going to look at functions s, s1, s2 which are non-negative simple measurable functions. Alpha will be a real number, alpha bigger than or equal to 0. Then we are going to look at what happens to various properties of. So, first observation is that integral s d mu is a non-negative number, it could be equal to plus infinity. So, integral s d mu is an extended non-negative real number. That is obvious because what is s d mu? Integral of s d mu is summation of a i's times mu of a i's, all the terms are non-negative. So, this is a non-negative number. So, this is an obvious property. The second property we want to check, that for a non-negative simple function s, alpha s belongs to L plus 0 plus, and the integral of alpha s d mu is same as alpha times the integral of s d mu. So, let us check that. So, s belongs to L plus 0 is a non-negative simple measurable function. So, let us write s is equal to sigma a I, indicator function of a I, where union a I is equal to x. So, whenever it is a partition, we will write as this square bracket union over I equal to x, and alpha is a non-negative, alpha belonging to R star, alpha bigger than or equal to 0. Then alpha of s, so has the representation, it is alpha a I chi of a I, and a i's are still a partition of x. But that means, if this is the representation, so integral alpha s d mu, integral of alpha s with respect to mu is going to be equal to, by our definition, I equal to 1 to n alpha a I times mu of A I, and this is a finite sum, non-negative everything. So, alpha comes out, alpha times the summation of I equal to 1 to n of A I mu of A I, and that is nothing but alpha times integral of S d mu. So, that proves the property that the integral of non-negative simple functions is if you multiply it by a constant alpha, then the alpha comes out. So, integral of alpha S d mu is equal to alpha times S d mu. Next, we want to show that it is a linear operation. So, we want to check that if S 1 and S 2 belong to L 0 plus, then S 1 plus S 2 belong to L 0 plus. That we have already checked, but we will check it again today also. And the integral of S 1 plus S 2 d mu is integral of S 1 plus integral of S 2. So, for such things we have, so let us take a function S 1 S 2 belonging to L plus 0. So, non-negative simple measurable function. So, let us write, let S 1 be equal to sigma A I chi of A I, where A I is form a partition of X, and let us write S 2 as sigma j equal to 1 to m B j chi of B j, union B j's partition of X. So, if you recall, we had said that we can bring the both S 1 and S 2 a common partition, and what is that common partition? A I intersection B j. So, what we are saying is you can write S 1 as sigma I equal to 1 to n, sigma j equal to 1 to m A I chi of A I intersection B j, and also similarly S 2 can be written as I equal to 1 to n sigma j equal to 1 to m of B j chi of A I intersection B j. Now, here note that union over I and j A I intersection B j, that is a partition of the whole space. So, that is equal to X. So, this is the point to be sort of noted, that whenever you are given two functions S 1 and S 2 with two representations which involve some partitions A I and partition B j, then we can bring them to a common partition, namely A I intersection B j. And now, we can define what is S 1 plus S 2. So, S 1 plus S 2 is going to be equal to sigma over I 1 to n sigma over j equal to 1 to n A I plus B j chi of A I intersection B j. That is clear, because on A I intersection B j S 1 is A I, and on A I intersection B j S 2 is B j. So, S 1 plus S 2 will be equal to A I plus B j on A I intersection B j. So, once we have gotten a representation of S 1 plus S 2, we can define what is the integral of S 1 plus S 2. So, this representation gives us that integral of S 1 plus S 2 d mu is equal to summation over I 1 to n summation over j 1 to m of A I plus B j into mu of A I intersection B j, right. So, because this is the representation, so A I plus B j is the value on the set A I intersection B j. So, the integral is going to be equal to summation over I summation over j of A I plus B j, the value on the set A I intersection B j. Now, the right hand side we can write split. So, that is equal to two terms, one is summation over I summation over j of A I times mu of A I intersection B j plus the second term summation I equal to 1 to n summation j equal to 1 to m of B j. So, A I and second term is B j mu of A I intersection B j. And now, these are all finite sums. So, we can write the first term as sigma I equal to 1 to n, take A I outside, and this is summation of mu of A I intersection B j, because this is summation over I only. So, we can take it out over j equal to 1 to m of A I intersection B j, plus here summation over j and summation over I. So, we will write it as summation over j first B j, and inside is summation over I equal to, I have interchanged the order of summation, they are finite terms only, finite sums only. So, that is allowed. So, that is 1 of mu of A I intersection B j. And now, we observe that the first sum by the finite additivity property of the measure is nothing but mu of A I, and this summation over I, this sum is nothing but mu of B j, because A I's form a partition of x and here B j's form. So, first term is equal to summation I equal to 1 to n A I mu of A I plus summation j equal to 1 to m B j of mu of B j. And now, clearly this is integral of S 1 d mu plus the second term is integral S 2 d mu. So, that proves the fact that integration is a linear process. Namely, integral if S 1 and S 2 are in L 0 plus, then S 1 plus S 2 also is in L 0 plus, and the integral is of S 1 plus S 2 is equal to integral of S 1 plus integral of S 2. Next property we want to check is the following, that for a set, if E is a set in the sigma algebra S and we multiply S non-negative simple measurable function by the indicator function of E, then that function also belongs to L 0 plus. That again we had checked it earlier when we defined non-negative simple measurable functions. So, its integral is defined and we want to check that E going to nu of E, which is integral of S indicator function of E d mu, is actually a measure on S. So, this gives a method of generating more measures on the sigma algebra E. So, let us prove this property. So, let us take a function. So, let us take a non-negative simple measurable function L plus 0 S of given by sigma I equal to 1 to n A I indicator function of A I, where union of A I is equal to x, and E is a fixed set in the sigma algebra S. Then S times the indicator function of E. So, multiply this equation on both sides by indicator function, that is I equal to 1 to n A I chi A I multiplied with chi of E. And now, here is the observation that the product of indicator function of two sets is nothing but the indicator function of the intersection. So, this can be written as I equal to 1 to n A I. This product indicator function of A I into indicator function of E can be written as the indicator function of A I intersection E. Okay. So, that is only observation one has to make. And now, so S times indicator function of E is given by this. So, where union of A I's intersection E, what will be that? That is a disjoint union giving you the set E, and on E complement this function is 0. So, if you like, you can add one more term here 0 times the indicator function of E complement, but that is not. So, normally whenever that kind of a set, that term will not mention it here. So, automatically on the complement it is 0, and that gives a partition of the set. So, this means S of indicator function of E is A I times indicator function of A I intersection E, where these things form a partition. So, that implies S times the indicator function of E is a non-negative simple measurable function. And what is the integral of that? So, integral of S chi of E d mu is equal to sigma I equal to 1 to n a I mu of a I intersection E. So, that is the integral of this function. So, we want to prove that if we call this as nu of E, that is a measure. Okay. So, let us check that property. To check it is a measure, what we have to check? So, nu of a set E is defined as sigma by our previous calculations a I times mu of a I intersection E, I equal to 1 to n, where a i's are partition of x and a i's are in the sigma algebra always. So, claim nu is a measure, right. So, what is to be checked? Nu of empty set equal to E is empty set. So, mu of a I intersection E, that is empty set. So, that is 0. So, it is equal to 0. Okay. What is the second property? We want to check nu is countably additive. So, for that, so let us write let E be equal to union of E j, j equal to 1 to infinity, where all the sets are in the sigma algebra. So, you want to show that, to show nu of E is equal to sigma nu of E j, j equal to 1 to infinity. So, that is what we have to show. So, let us compute both sides and show the required property. So, let us look at nu of E. So, nu of E is equal to sigma I equal to 1 to n a I mu of a I intersection E. By definition, right, nu of E is defined as this thing. Okay. And what is E? Let us put the value of E. So, it is I equal to 1 to n a I mu of a I intersection union disjoint union E j, j equal to 1 to infinity, right. That is by the definition of by the fact that E is a disjoint union of E j's, but that we can write it as summation I equal to 1 to n a I mu of. So, this is nothing but, so we can write it as disjoint union over j 1 to infinity of a I intersection E j, right, by the distributive property of intersection over union. So, this is a countable disjoint union of sets in the sigma algebra. So, by the countable additive property of the measure mu, this term is equal to summation I equal to 1 to n a I summation j equal to 1 to infinity of mu a I intersection E j, right. And now, note that we have got two sums here, one is summation a I, another is summation j equal to 1 to infinity, and all are non-negative extended real numbers. So, we can interchange the order of integration without any problem. So, we can write this as summation over j first, then summation over I 1 to n a I mu of a I intersection E j. Okay. So, we write this as this. Now, note that this the term summation over I a I mu of a I intersection E j is nothing but the nu of E j, right. So, by definition this is summation over j equal to 1 to infinity. So, this is nu of E j. So, we have shown that nu of E is summation nu of E j's whenever E is equal to union of disjoint pairwise disjoint sets E j. So, that proves that nu is a measure. So, we have proved this property also, that for a set E in S, the integral s times indicator function of E is a non-negative simple measurable function, and if its integral is denoted by nu of E, then nu of E is a measure as E varies over measurable sets. And this measure has a very nice property. So, this new measure nu of E has a very nice property that nu of E is 0 whenever mu of E is 0. So, let us just check that property again, check that property. The nu of E is defined as summation I equal to 1 to n a I mu of a I intersection E, where union of a i's is equal to x. So, if mu of E is equal to 0, that will imply that mu of each a I intersection E is also 0, because a I intersection E is a subset of E and mu is a measure. So, mu is also monotone, right. So, mu being monotone, mu of a I intersection E is less than or equal to mu of E, which is equal to 0. So, that means this is equal to 0. So, implies nu of, so each term in the definition of nu of E is 0, that means nu of E is 0. So, this new measure, which is defined via integration of non-negative simple functions, has the property that mu of E equal to 0 implies nu of E equal to 0. This is a very special property. So, it relates two measures mu and nu. That means, it says whenever E is a set of measures 0 for mu, it is also a set of measures 0 for nu. And later on, almost in the end of the course, we will characterize such measures. Whenever two measures are related by this, there is a theorem which says that nu must be representable as integral with respect to mu. So, we will come to that theorem a bit late in our course when we have finished integration and some more properties of it. So, this nu of E, which is written as which is an integral, is having a special property. And let us also mention that integral of s indicator function of E d mu is also written as integral E of s d mu. So, this is another way of writing. So, this is called integral of s over E. Okay. So, we say this is integral of s over the set E. Okay. So, that is the notation will follow, because outside E s is 0 in this representation.